Hello everyone, welcome back to this exciting chemistry lessons. My name is Andrana Linda Bazoka Prophet, and in today's video we are going to be talking about more questions on coordination chemistry. Right now, in our previous video we did part 1 of this video, so in part 2 we are going to be talking about more and more questions. Now the questions on the board is saying anhydrous copper 2 sulfate is white, why hydrated copper 2 sulfate is blue. Why is this, or why is it like that? Actually, it's very simple. Now we should understand that water is a ligand, and ligands are like Lewis bases. Why, or what happens to them? Ligands are small molecules that are bonded to transition melters, and when that happens they tend to form a bond, and that bond is called the dative or the coordinate covalent bond. Now we should understand that the reason for many colors of complex compounds is due to ligands, or is due to the splitting of the d orbitals. We should understand that the d orbital has 5 degenerate orbitals. 5 degenerate orbitals. Now, when it approaches a ligand, the ligands tend to split the d orbital of the transition elements into 2 sets, according to the splitting effect, to crystal field splitting into the lower energy and the upper energy. Now this question says, why is anhydrous copper 2 sulfate white? The answer is simple. Anhydrous copper 2 sulfate has no water ligands, but in the case of hydrated copper 2 sulfate, it has the water ligands, which will result in the splitting of the d orbitals, resulting in what we call the d-d transition. The d-d what now? Transition. Is that okay? Now that is just simply the answer. There is no water ligands in anhydrous copper 2 sulfate, while there is a water ligand in hydrated copper 2 sulfate, which will result in the splitting of the hydrated copper 2 sulfate into the lower energy and the upper energy, according to the crystal field splitting, or according to the crystal field theory. Now we'll move to the next question. Number 2 question says, which of the following is more stable complex and why? Simple. Now the name of this complex is called hexaamine cobalt 3 ion. Why this compound name is called tris-ethylene diamine cobalt 3 ion. Now you are being asked which among these two is stable and why? Simple. This tris-ethylene diamine cobalt 3 ion is more stable compared to this one. The reason being that ethylene diamine, right, is bidentate, meaning it has 2 teeth, or it has 2 donor atoms. Is that clear? It has 2 donor atoms, and because it has 2 donor atoms, which is the nitrogen atom, for example, this is the structure of ethylene diamine. It is like this. So you could see these two nitrogen atom here supply the electrons, tending to form a ring form. So the formation of a ring form, right, aid in the stability, what we call Chelate effect. It means that this one, because it can form ring, it has to do what we call what now? Chelate effect. It can form a Chelate effect, right? But this one is monodentate. This can't form ring, but this can form ring. If you look at the structure of it, if this is cobalt, you'll be having this, meaning this nitrogen atom here will be bonded to this one. This other nitrogen atom here bonded to this one. So the same thing here, En here, same thing here. So you could see, you see a ring form. This is what we call the ethylene diamine. Ethylene diamine. Each ethylene diamine has 2 donor nitrogen atoms, which they use to bond to the what now? Cobalt. And that is how easy this answer is for number 2. Now we'll move straight down to number 3. Let me quickly wipe the board. Now, in the case of number 3, because they say find coordination number of the following what complex. Now we should understand what is coordination number. Simple. Coordination number simply talks about, or simply means the total number of ligands, right, that is attached to a transition melter, which is very, very simple. Now, if you look at this one here, this one is tris-ethylene diamine cobalt 3 chloride. Cobalt 3 chloride. Now, look at this diagram here. Remember, you are asked what is the coordination number of this complex. Now, please take note. The coordination number of this complex here is 6. Why? The total number of donor atom, right? Remember, in number 2, I drew for you the number of the number of donor atom in ethylene diamine, meaning one ethylene diamine, because it is bidentate, supplies water. Each of the nitrogen atom in ethylene diamine tend to supply nitrogen, their lone pair of electrons, which will complex with what now? The cobalt. Exactly. So for every ethylene diamine, it supplies 2 donor. 2 donor what now? 2 donor atoms are involved, which is the nitrogen atom here. So if I'm having 2 here for 1, if it's 3 here, right, it will be 3, 2 times 3, which is what now? 6. So in the case of this one here, you have 6 coordination number, right? While in this case here now, remember this fair here, you are not looking at for the, this is not the ligand, no, this is outside. Exactly. Now you're only considering the ligands are always in a sphere, in a what we call a coordination sphere. So you're only considering what is inside this bracket. This is what we call the coordination sphere. So here now, here is 2 and here is 2. So the total number of coordination number here is what now? 4. That's 2 plus 2, 4. But in this case here now, here is what now? 6. 4 plus 2 is what? 6. And this marks the end of this our second part of our questions on coordination chemistry. Please do well to like, subscribe, and share. And also do well to share to everyone you know. For now, God bless you. Thank you.